It works. Hello, good evening everyone, and it's using the wrong camera. Anyway, good evening everyone, welcome to Physics with Keith. If you're tuning in for the first time, you've never seen this before, then this is the live Tuesday evening tuition session, and it's interactive, and you can interact by going to the Discord channel, and you can see a few people have been dropping their messages off over there. I'm just going to switch my webcam over for a second so my face will freeze. So if you go across to that Discord channel, then you will see Discord, what's this called? It's not called a channel, is it? What's it called? Server. Go to the Discord server and you'll see there's all sorts of channels. The one you want is the one that's called Season 4 Episode 5, and today we're going to be looking at the gas laws. It's the last time I did gas laws on a tuition session was last summer, so it's been nearly 6 months since I last did it. So yeah, it's about time we did it again. Right, just having a look and making sure all my camera settings are right. A friend of mine has passed me a camera to use, a new camera to use, which is very kind of them. I've never used this camera before via OBS. I've used it in a meeting before, but not via OBS, so hopefully it will look a little bit clearer and the darks will be darker and the colours will be brighter. We'll see. It's my first time using it on a live thing, and straight away the software I used bounced across to the wrong webcam, so I'll have to fiddle around and work out why it did that next time. Anyway, just press that button there and we're good. Right, well I really hope that's not the case. Let's just check and see if it's not trying to detect sound in the wrong place or something silly. No, it's only supposed to be detecting sound through my microphone. Interesting. Okay, well I'm sorry to anyone that's tuning in new for the first time and doesn't know what's going on. I suspect I've still got it set up for something else that I had. So let's just go into settings. I will start in a minute, but I might as well get it right. I had a meeting and I might have adjusted some of my settings for that meeting, you see. So open sound settings. Manage sound devices. Right, how's that sound? Yeah, okay, well I'm not going to fiddle with it now, I'll have to fiddle with that later. That's really disappointing. It's better now. Okay, it's disappointing that I had to fiddle with it at all. What an unprofessional start to this session, but I guess you get what you paid for. So it's not too bad. No, but I want it better. I'm always in the quest for things to be better, so never mind. Right, yes, gas laws. Let's get cracking then. Now I have two things that I want to dig into today. The first thing is unit conversions, because you're going to have to be fluent with your unit conversions, and the second thing is how to apply those gas laws in the most if I say sensible, that's a nice vague word, but you know what I mean, the most sensible way. In other words, we don't just want to start throwing the full ideal gas equation at every problem. There are better ways of solving questions if you know which of the experimental gas laws to use. So they're the two things I want to look at today. And so we'll start with some unit conversions. And what I've got is a drill spreadsheet. If this is your first time tuning in, then I have a number of spreadsheets that I've written that generate questions, and you have access to them if you've become a regular participant, and you know, your name appears several times down here in the chat thing, then your name goes yellow, and you have access on Discord to a special channel where you can download various drill spreadsheets. Yes, as Jonathan correctly points out, swag. So so what you're seeing now, if you're a regular participant, you can get this for free just by going straight onto that Discord channel. So here we go. Here's the first one, and the way all these drill spreadsheets work is you get given a bunch of questions. You can see these here, and then if you, well, apparently it is poggers, and if you hit F9, you get a different set of questions, and so on. Oh, hello, 𝗭𝘬𝗫𝗁𝘁𝗶𝟐. That's a name I don't recognise. It's good to see you. Freya also agrees it's this is a word that people know apparently. Poggers. Okay, I only learnt it a few weeks ago from my year 12, so we're keen to teach me what poggers meant. But okay. So, or maybe it was on here actually. Anyway, so the way it works is you've got a question, it asks you to convert. In this case, it's a volume to a volume, then a length to a length, and it's just to make sure that you can understand how to use your unit prefixes when the units are squared or cubed, and also that you know what the prefixes are. And that's a skill that you need for GCSE physics, and it's a skill that you will still need for A-level. Yes, Pranav points out we all learn something new. I learn slang that is being used by the youth, and you learn a bit of unit conversions. Anyway, if you click answers at the bottom, you get the answers. So what I'm going to do, I'm going to give you a few minutes. I'm not going to give you too long. I'm going to give you a few minutes just to try to work through on a piece of paper these unit conversions, and then I'm going to ask you what you got, and we'll see whether you got what I got. And hopefully you did. The first one's quite an easy one, to be fair. But don't type any answers yet. Just work it out on a piece of paper, see how far you can get. If you're confused that it goes 1 to 8 and then starts at 21, it's because if you scroll down, there are loads more. But anyway, we'll leave it there. So see how many of them you can get right, and I'll just sit here for a few moments, looking awkward. It's picking up a lot of background noise on my microphone, isn't it? Yeah. And I think I know why. If I've had an update to my graphics card, it knocks off the thing I'm using that loads a VST. By the way, I don't know what all these words mean. Which cuts out that background hiss, so it's picking up my background fan, my computer fan. I'm not going to fiddle with it now. I'll fiddle with it in about 50 minutes time when we finish. So how many of these have you managed to get done so far? We've had a couple of minutes now. How many of these have you managed to get done? The first 4? That's pretty good. Yeah, okay. First 2, okay. if you're watching this live, do make sure you're live. It should say live in the bottom left corner, I think it is, of your YouTube stream. If it doesn't say that, then you're not quite live. Or if you know, when you press it and the live appears. If it doesn't, then just make sure you fast forward it to the point where you're live. Otherwise we'll be forever behind. The other thing is, I've noticed that YouTube by default seems to bump the video quality onto 144p. If you just go into where you select in the options, you select the video quality, select 180p, and the video will clear right up. It won't fix my sound issue, but at least the video will clear right up. Okay, why did I say number 1 would be a nice easy one? Anyone happen to know? Exactly, yeah. Exactly right, yeah. So 84 cubic centimeters is 84 milliliters. Yeah, no, I mean, that's right. I need to find a better LaTeX interpreter, because this is really struggling with this, isn't it? Always goes off the edge of the screen. All things I'd like to get round to doing and don't quite have time to do. So I'm just going to take a little screenshot of this, of these questions, so I can write the answers next to them as we go along. Let's choose a blue pen, shall I? Right, so the first case here, we know, okay, 84 milliliters, no calculation necessary. And whether you use a capital L or a lowercase l, it actually doesn't matter. They're both acceptable. Now 96 nanometers, that's 96, and I'll put the decimal point there because that's going to be helpful. In fact, what I'll do, planning ahead, I'm going to give myself a bit more room. I'm going to write 96 all the way over here with my bullet, with my decimal here. I'm going to think ahead and put a whole bunch of zeros in here. I don't know how many zeros I'll need, he says, as though he doesn't know how to do it. So I'm just going to put a whole bunch of zeros in here. This is not the most, the best way of doing this, but it works. So let's start by getting from nanometers to meters. If we get from nanometers to meters, then the number's going to be getting smaller. And so each time we move by one letter of the prefix, we move by 3 places of the decimal place. And you need to remember those prefixes. I'll write them across the top in case that helps out. We've got, starting from the middle, going up, kilo, then mega, then giga. Then we can keep going, tera. We go downwards. We've got milli. I'm not going to put centi in here, that's a special one. Micro, nano, and we keep going down here, pico. Now leave it there because that's as far as this thing goes. A-level students, you need a bit more than that. But it's the same strategy. So we're going from nano, which is here, and all the way up to kilo, which is there. So we are going to go, so 1, 2, 3, 4, 5, 6, 7, 8, 9. We need to move the decimal place. 1, 2, 3, 4, 5, 6. I've missed one. Shouldn't be 9. I've forgotten 1. Someone tell me what I did wrong then. Before I've actually fixed it. There we are, the no prefix. Exactly right. There it is, missing there in the middle. So nano, so it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's better. So we move the decimal point 12 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Put the decimal point there. I mean, what a mess. But it works. So now I'd write my answer down as 0 point. How many zeros do I need? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think that fits on the screen. And then 9, 6 on the end. What a mess. Of course, there's a more sensible way of doing it, and that's to do it in standard form. So what you could say is, and I'm not going to use standard form, I'm going to use multipliers. I'm going to say 96, and I'm going to say this is times 10 to the minus 9. That's what nano means. The minus is in the wrong place there, AVAX1 USS. But I think, yeah, I think the minus is in the wrong place. But apart from that, I think that's okay. I think. So you've got this. We want to turn it into kilo. We're going to the right. So we need to make this number smaller by 10 to the... let's get this the right way around. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's get rid of that one there. Our answers are pouring in. I'm not keeping up. I'm desperately trying to keep up with what I'm doing and what people are writing, and I'm really struggling. Pranav, I agree with you, because that's exactly what I just wrote. Avax, I think your number's wrong. Pranav, your answer's gone off the edge again. Dvorak, yes, you got the same, which is what I got when I wrote the zeros out. Kessia got the same, Joe got the same, Wombat got the same, so I think we can all agree Avax is wrong. I'm not quite sure what he's done there. People are still going to write, it's still going to distract me. But listen, if you've got a calculator with a special button on it, oops, it's frozen up. If you've got a calculator with a special button on it, and you might have a calculator that has the eng button on it. Anyone got a calculator with an eng, an ENG button? This is going to be a tremendous help to you. Yeah. Because what that will do is it will bounce in multiples of 1,000. Yeah. Not all, Joe. Not all Casios. And there are better calculators out there. Don't get me started. So that will, you can use eng mode, engineering mode, and bounce the decimal place in powers of 1,000, up or down. And I can't remember on your calculator whether it's second function and eng to bounce it one way and eng to bounce it the other way. But the nice thing is it will show the same number, so it really doesn't matter. And so what you're trying to do is get your number, which has here 96 times 10 to the minus 9. You want to put it, so instead it's got times 10 to the 3. And so the question is, how many places do I have to move the decimal place to get the multiplier to go from 10 to the minus 9 to 10 to the 3? And you don't even have to think about it if you've got the eng button. You just keep pressing it until you get to 10 to the 3, and the number that's displayed will be the number you want. Otherwise, what you're basically saying is, what is this number here? To get from this to that. And that's just algebra. You know, this is just algebra. If you look, this bit here is nano, this bit here is kilo, this number on the left, this number here has to equal this number here. That's what the equal sign means. So what goes in this missing box here? Well, if I just divide the left-hand side by 10 to the 3, it gives me 96 times 10 to the minus 12, or 9.6 times 10 to the minus 11, which is what you were all saying, which goes into this box, and I put kilo instead of times 10 to the 3. It means the same thing. So mine doesn't, at least, the calculator doesn't do such a small number. Oh, does it not? Are you telling me there's a defect, a drawback to having a Casio? Well, how about that? My calculator does it perfectly well. This method I quite like, actually. I think this method is the best one to use, because it takes away any sort of guesswork or counting decimal places as you bounce it along. Yeah, who would have thunk? So what we're going to do is we're going to do that again. This is nano, this is pico. We're going to do it for this one here. So watch closely. 70 times 10 to the minus 2. I've written that because times 10 to the minus 2, that bit there means centi. Notice I'm not bothering with the meters here. I could have put an M here, but then I'm going to get confused with milli, so I'm not going to put the unit. I'm just putting the prefix. 70C is the same thing as 70 times 10 to the minus 2. That has to equal some number that I'm trying to figure out, and then micro. And I remember that micro is times 10 to the minus 6. And you've just got to remember them. But they go up and down in multiples of 1,000, so that's okay. So how do I work out what number goes in this box here? I type into my calculator 70 times 10 to the minus 2 divided by 10 to the minus 6, or I know a bit of maths, and I can see that this is the same thing as 70 times 10 to the minus 2 times 10 to the 6, which means it's 70 times 10 to the minus 4. So the number that goes here is 70 times 10 to the minus 4. Notice I'm not putting it in standard form, I'm keeping that 70 as it is so I can keep track of what on earth is going on. No minus, thank you. You're quite right. 6 minus 2 is not minus 4. So, yep, thank you very much. Yep, 70 times 10 to the 4. I can do 6 minus 2 apparently. Maybe I can't. So there we go. And then if you want to write that out full, you can. Or if you want to leave it in this form, you can. Or if you want to make it standard form and say 7.0 times 10 to the 5, you can. It doesn't matter. The number's right, and now you've got the prefix to match. So those first 3 examples were quite straightforward. The first one, because the units are equivalent. The next 2, because they were just lengths. The next one's where it gets a little bit more tricky. So hands up, not hands up, I can't do that. Let me know if you did number 4, if you had to go at number 4. We will go on to some gas laws, but we need to be able to convert units first. So who got on to number 4? Yep. Yep. Freya didn't. Okay, that's okay. Lex is French. Anita did. Well done. Wombat did. Okay, so let's have a look at number 4. The tricky thing now is that this square doesn't just refer to the unit, it also refers to the prefix. It's not just meters squared, it's kilometers or kilometers squared. So that's kilo squared times meters squared. And I'm going to strip out the meters squared part and ignore the meters squared part because that's here and here, and I can add that on later. Basically, I'm dividing both sides by meters squared. But I'm left with kilos squared and milli squared. The squared is there. Our notation doesn't write it, and I wish it would. So I'm going to leave it written like this, because that might make it a bit easier to see what's going on. 51 times the kilo is squared. Kilo was 10 to the 3, but it's squared. Now we're going to convert that into... I need some number to fill in this box, times by milli, which is 10 to the minus 3, but that's also squared. So now I need to figure out what to put in this box. 51 times 10 to the 6, that's what 10 to the 3 to the power of 2 is, I hope. And then 10 to the minus 3 squared is 10 to the minus 6. That becomes 51 times 10 to the 12, or 5.1 times 10 to the, which way around do I go? 10 to the 11. I've gone the wrong way there, haven't I? 13. Yeah, I thought I went the wrong way. Thank you. Glad you're all here. And that's in square meters. And don't forget the meters is squared as well. Yes, it is Wombats. It's funny, Pranav got there first. He was the fastest. 𝗪𝘳 and 𝘭𝘪𝘯𝘬 were quick on his heels. And Wombat, because you took the time to make it into a sentence, he came in last. Anyway, there we go. So you can leave it in this form, or you can write 5.1 times 10 to the 13, or you could write 5100000000, just add 12 zeros. You know, I wouldn't. That is up to you. So as a method, came last in. No, I don't think Wombat came last in style. I reckon Wombat came first in style. In fact, if Wombat included a question mark, it would have been perfect. Okay, so Exactly the same thing for the next one. I'm not even going to bother doing the next one because the next one is the same unit to the same unit, so there's just no point me doing it. But you'd follow the same approach. Pranav, you can, but it's not advisable to ignore the examiner because they're going to spend about 4 seconds per mark point deciding whether you get the mark or not. And if they're spending that 4 seconds trying to interpret whatever gubbins you've written, they're not going to be grateful. Right, let's just have a look at number 7. Moles is straightforward, James. Moles doesn't need a lot of brain power, really. When you write mole, you're just writing Avogadro's number. That's all that is. Mole equals Avogadro's number. Yeah, it's just a number. So 3 moles is just 3 times Avogadro's number. It doesn't need to be difficult. And you don't deal with moles squared or moles cubed. So the conversion is very, very straightforward. Whereas, you know, these sorts of conversions can be a bit trickier. Oh, I see what you're saying, James. Yeah, don't write it out in full. Use standard form with moles. Use standard form when you're dealing with numbers of that sort of size. Okay, question 7. There's a trick in question 7. And it's a trick. It's not that tricky, really, but people miss it. People sort of fall for this. And as I can see, yet again, OneNote is conking out on me. Bad day with my computer today. Stand by. I'll just bounce back out and back in. There we go. So 92 cubic centimeters. Yeah, it'll take a while to write and a while to read. Yeah, exactly. There we go. Dvorak, I think the way you've written it's perfect. 92 cubic centimeters. My first step would be to put that in milliliters, simply because then I can see the milli is here, and I'm trying to convert that to some number in liters. And I'd write 92 times 10 to the minus 3 liters equals some number of liters. It's done. That's it. 93 times 10 to the negative 3, or 92, or 9.2 times 10 to the negative 2. I've got that the right way round. Yes. So that's pretty straightforward. Right. Let's try a volume one then. So if I go back to the questions we had, there was a volume one up here. 21. Did anyone manage to answer question 21? Anyone managed to answer question 21? Well done, Pranav. Yep. So question 21. 54 cubic meters into cubic millimeters. I'm just going to write it down. 54 cubic... Was it cubic meters? Cubic meters into cubic millimeters. And I'm going to put the milli cubed as well. Yeah, well done. So, same thing as before. I can ignore the meter cubed part. I'm going to have that on my answer anyway. I'm not bothered about that. It's the milli part, milli cubed. So this is equal to some number I need to fill in. 10 to the minus 3 cubed, meters cubed, is 54. Yeah, so I'm going to write 54, exactly. So I'm going to write 54 divided by 10 to the minus 9, which is the same as 54 times 10 to the 10, oh, sorry, 10 to the 9, which is the same as 5.4. Move the decimal place to the left, so we increase the power. 5.4 times 10 to the 10. And the the meters cubed, the unit part is still there. I just didn't bother writing it for the rest of this, otherwise I'd get it confused with milli cubed, so I left it off. It's inconvenient having m for million, m for meters, but I didn't invent it. I think we're okay now. So the reason why you need to be able to do these sorts of conversions is because you you could be given an area problem with pressure. We're not going to look at those today, but we might look at those next week. Or you could be, if you wrote E in the exam, would it still be correct? Isn't it some constant? Oh, I see what you mean. So, Kessia, I think you're asking about the notation that Matthias is used. That would be fine. I think that would be fine. It's an acceptable. I wouldn't recommend it, but it is an acceptable notation. Yeah, Pranav, it's mostly for historical reasons. So on a computer, if you were writing a power, one way of doing it would be to write sort of exp, and then what you put in brackets is the exponent of the power of 10. The base is 10, and exp is the exponent for that base of 10. So that's a pretty normal way of doing it. On old calculators, for example, you won't have a button that says 10 to the power of x or anything like that. You'll have a button that says either exp, or it might say ex, or it might just say e. So I've got calculators with it written in all these different ways. Entering things into a computer with powers, I mean, I don't know how you would ever do that. So it was decided long ago, back in the 1960s or 70s, that they would use an E to mean a power of 10. It doesn't really answer your question, but that's the answer I'm given. Yes, Pranav, it is a constant, and the way you don't get it confused is context. In the same way as we don't get this confused. I've left an mm, but I understand that's not meters. I understand that's millimeters from context. No one would write 5.4 E10 to mean 5.4 multiplied by Euler's number multiplied by the number 10. No one would write that. You could, but you would be a very strange individual to do that indeed. Whereas it is an accepted convention because of computer programming to write your powers, to write your standard form or any number where you need a 10 to the power of using this notation. Me personally, I'd actually put a capital E there, but that's because I've been indoctrinated with Excel, Microsoft Excel. But they're both acceptable. And if you ever use 𝗂𝘃phys, then you'll use that notation all the time to put numbers into 𝗂𝘃phys. So I don't think it's easy to confuse it because of context. Right, so areas. You'll need to be able to convert areas because pressure is force divided by area. You'll also need to be able to convert volumes because very often, especially in A-level, gas laws questions don't have a nice convenient unit for volume. So here's another drill. I'm afraid it's not a pretty looking drill, but it works. As before, if you hit F9 on a keyboard, you get different questions. And you can do a few things in this drill. If you click settings, you can choose, for example, keep all my temperatures in degrees Celsius. If you just delete that, it'll only give you temperatures in degrees Celsius. Or if you choose that option, then it will let you have temperatures in either unit. The same with this. Will I allow milliliters or not? Will I do an amount measured in moles or molecules? By the way, don't just say amount in an exam. It's okay to think about it in terms of amount. It's okay to write that down, but in an exam context, you'd have to be a bit more specific. And then you can choose either to ask questions just about Boyle's law, just about, so you put the 1 if you just want Boyle's law. If you want Boyle's law and what we call the pressure law, that's 𝗂𝘃-Sachs law, then you'd do 2. That gives you the first 2. And that's as far as you need to go at GCSE level. So questions, 2 in that box there if you're GCSE level, with either of these units, molecules or moles, it won't matter. You won't get questions where it's relevant, but you will have to be able to get answers in numbers in degrees Celsius. So the setup as it appears on the screen there is a sort of a GCSE level setup. Charles' law is A-level, and so is the ideal gas law in all its forms. So if you want all of the equations, you hit 4. And that's what we're going to try. That's what we're going to try. Along the bottom you see there's a tab that says questions. You get a question, question 1 for example. You now know what this notation means with the E. We've had a discussion about that. If you can't work out which law is being used, you click with hints and it will tell you. So the first one, you can't solve it without using the ideal gas law. The next one, you solve it using Charles' law, and so on. And then finally, if you want your answers, you click the Answers tab and scroll across, and it gives you the answer. So that's how this is going to work. Let's hit F9. This looks like a good mix of questions. See how many of these you can get done, and I'll give you a little bit of time, and then I'll go through a few different ways of solving it. And I'm going to distract you while you're working by asking you a question, which is, I know the sound quality isn't as good, and I can see that on my audio mixer. What about the visual? What do you think? We're comparing this camera that you're currently looking at. Very good. Yeah, to the previous one. Yeah. As I say, it's a very generous gift from a friend. Maybe let's get them back. It's a very highly rated webcam, which was unavailable for a long time because of COVID. Everyone went out and bought webcams. Again, I'll talk to you and distract you while you're working. Really happy. Not on Sunday, on Monday, I think it was. My number of subscribers on the channel reached 500. Really, really happy, really happy. Thank you so much, everyone. It is the best way to support what I'm trying to do, is to subscribe and encourage your friends to participate and subscribe as well. You can see it's everything goes much better when more people join in. I'll make this little silly animation go rolling across the bottom of the screen. There we go. Courtesy of PowerPoint. So the first 3 questions, I'm quite glad these came up. The first 3 questions all test a different, what we call experimental gas law. The experimental gas laws assume that a gas is a continuum, not a collection of discrete particles. It treats gases as continua. What's nice about the first 3 questions, by the way, is you don't have to do any unit conversions whatsoever. I mean, you'll have to do unit conversions for ideal gas law. And if you ever get a temperature in degrees Celsius, like you can just see question 9 just poking out at the bottom there, has a temperature given to you in degrees Celsius, you'll have to turn that into Kelvin. You can't use any of the experimental gas laws or the ideal gas law unless your temperatures are in degrees unless your temperatures are in Kelvin. But those first 3 questions you can just answer straight away. So has anyone managed to do the first 3? Definitely want to go through the first 3. No one yet. Okay. Oh, Pranav has. Wombat is on the 3rd one. Good. Trying something out. Hey, it worked. That's an intense looking face. Okay, I'm going to take a screenshot of the first 3 and I'm going to we're going to go through worked solutions to the first 3. And then hopefully next week we'll have a go at some exam questions. I didn't want to go straight to exam questions this week. I wanted to get the skills right first. Oops. As you know, my arithmetic is not great, so expect me to make mistakes here, but you're welcome to pick me up on them, please do. Let's start with question 1. Who's done question 1? Great, great, super. Okay, so, yep, brilliant. So we have, why is it not saying that anyone's typing? Maybe it's because it doesn't have focus. Anyway, okay. So we have, well, we've been told pressure and volume. And a few variables have not been mentioned. One of the variables that's not been mentioned is temperature. So this is the case where temperature is constant. Now, if temperature is kept constant, then we are using Boyle's law. I'm afraid you've just got to learn that. You just have to remember that constant temperature is Boyle's law. Because, you know, it could appear on GCSE or in A level. The mnemonic I use to remember it is that as water boils, its temperature doesn't change. I know it's a different spelling of the word boils, but it helps me remember it. So, we could write Boyle's law as, well, it doesn't matter which way around we do it really. We could write it as pressure is equal to some constant, I'm just going to call it K, multiplied by temperature, but that has to be an absolute temperature. What we're saying is that pressure and temperature are directly proportional. It only works if temperature is measured in Kelvin. And you can get a feel for this. You can understand this is true. If I take a sealed, hang on, that's not Boyle's law. What am I writing? None of you corrected me on it. Boyle's law. Let's try that again. Pressure and volume are inversely proportional. So pressure inversely proportional to volume. There we go. Yeah, I'm not surprised, Pranav. That's what happens at 6:45 after, well, I'm not going to make excuses. I'm just a terrible physicist. Okay, so pressure times volume is a constant. Pressure is inversely proportional to volume. There we go. That sounds more correct. So you can get an idea, you can see that this is kind of true if you take, for example, let's take a balloon. If I take a balloon and I put air in it, so I've got a certain volume of air, and it's at a pressure equal to atmospheric pressure, sure. If I compress that slowly, somehow, I put it into some sort of way of compressing it slowly, I understand what's going to happen is the pressure is going to increase on the edges of that balloon. And if there's a little bit where the balloon can bulge, it will bulge outwards because the pressure will be higher in that place. The temperature will be the same because I'm doing it slowly so that any heat that would accumulate has time to dissipate. It didn't, Pranav, I hope. That's right. So, Boyle's law, constant temperature, here we go. So, two ways of solving it. Way number one, you calculate the constant for the before times, and then you use that constant to calculate the situation in the after times. It's a bit of a long-winded way, but we'll do it. We'll work out that the constant is going to be equal to the pressure in the before times, 4.847 times 10 to the 5, multiplied by, now you're going to say but the volume in the before times is in milliliters. It doesn't matter. As long as the unit I use for my volume in the after times is the same, it doesn't matter. So that's why I said I don't need to do any unit conversions. Now if I type that into my calculator, I get a constant. I don't know what that constant is. I haven't bothered to calculate it yet. Let's see if I can calculate it. Probably not faster than you lot because you've got younger fingers than me. Okay, well, given that I think I typed the first number wrong, I'm not trusting that. I'm going to try that again. Oh no, I've got the same number twice, so maybe that is right. Still not happy with it. Oh, it's because I'm in Eng mode. That's why I'm getting confused. Put my calculator in Eng mode. I wonder, I don't know what's going on. Right, so that gives me, let's put it in standard form, Charles. So 3.921, let's do 4 significant figures, times 10 to the 11. And the units are going to be, I assure you I am not using a Casio. And the units are going to be, have a look at the left hand side, you must include the unit, Pascal, milliliters. That's the unit. So now I've got what K equals, I can use it to solve the volume afterwards. Volume afterwards is going to equal that constant we've just calculated divided by the pressure. So that's 3.921 times 10 to the 11 Pascal milliliters. I'm going to write the unit in there just to be difficult. And then that'll divide that by the pressure afterwards, which is 2.362 times 10 to the 5 pascals. You'll notice the pascals cancels, and we'll be left with units of milliliters, which is what our final volume will be measured in. So if I type in 2.362 E5 divide, it gives me an answer of 1.660 times 10 to the 6 milliliters, or 1660 litres. Yeah, exactly, Matthias, exactly right. So that's the long-winded way of doing it. Calculating that constant, then using that constant. There's a quicker way. Let's just rub that off. Again, this is GCSE and A-level. Boyle's law appears on GCSE and A-level. The quicker way is to use the expression on the right-hand side. The fact that they're inversely proportional means that the inverse of the proportional change in pressure is equal to the proportional change in volume. What we're essentially doing is saying that pressure before times volume before equals pressure after times volume after, rearranged to make volume after the subject, and then just plug the numbers in. That's essentially what we're doing. So let's look at the proportional change in pressure. The pressure after is 2.362. I'm not going to bother with the power of 10 because it's the same as before. The pressure before is 4.847. I take the inverse of that and then I multiply it by the volume before. Don't write it like this. This is not a standard notation. And that gives me my volume afterwards. I take the inverse because they're inversely proportional. So whatever the proportional difference is, I take the inverse of it and multiply that by the original number. It's a much more straightforward way of doing it. Right, who tried question 2? Few of you? Yeah, great. Okay. So with question, I have to say the latency, the delay on Discord is far lower than I experienced on YouTube. I do like it. So, and also there seems to be a lot of people, I say a lot of people, there's a few people, but they're asking a lot of questions on the physics Q&A section. You know, you can all join in and give answers. Don't just leave it to me. It's a community channel. So if you see someone's asked a question on the Discord channel about physics, you go ahead and put an answer. Don't wait for me to do it. Sometimes it can take me a long time to get round to it. So we've got temperature listed and we've got volume listed. And I'm just going to erase the highlighter pen from the previous question so we don't get confused by what's going on. There we go. And the thing that's not listed is pressure. So this is a constant pressure situation. And it's broken on me again. Let's go back. There we go. So a constant pressure. If it's a constant pressure, then it's Charles' law. And I'm afraid the way I remember that, I think the apostrophe is in the wrong place. I think it should be after the S. The way I remember that, it's a bit embarrassing. I remember Boyle's law because temperature doesn't change of water while it's boiling. So I know temperature constant has been dealt with. I know the pressure law can't have constant pressure because that would just be a rubbish name for a law where nothing's changing. Pressure law, where pressure doesn't change, is a rubbish name for a law. So I know the pressure law has a changing pressure in it, which means that constant pressure is the other one, Charles' law. And that genuinely is the way I remember which one Charles' law is. As a 37-year-old, very experienced physicist, that's how I remember it. So whatever mnemonic you need to use to remember this, you go for it. Now, volume and temperature are directly proportional. That's what Charles' law says. So if I have a constant pressure situation, maybe it's a syringe with a plunger that can move in and out freely, and I change the temperature of the gas in that syringe, I reduce it, then the syringe will contract, the volume will reduce. And if I measure my temperature in degrees Celsius, then this isn't going to work. They're not going to look like they're directly proportional. So I have to make sure my temperature is measured in Kelvin, and then if I halve my temperature, I halve my volume. Unfortunately, the good news is the temperature is given to us in Kelvin, so that I don't have to do step 1, which is convert temperature. Two ways of doing it. We can write this like this, solve for K, and then use that value of K in a subsequent calculation. Or, because they're directly proportional, we can say that the proportional change in volume is equal to the proportional change in temperature. So the volume afterwards, divided by the volume before, the units are the same. They've got the same power of 10, so I'm not going to bother writing that power of 10. I'm going to be lazy. You can actually get away with being lazy like this in an exam. You can do this. They're not going to deduct a mark if you've done it right. If you're nervous about it, go ahead and put this. But it doesn't matter, they're cancelling anyway. And that's the proportional change in the volume. Multiply that by the temperature in the before times, and that gives you the temperature in the after times. And someone's going to very kindly tell me what that is now while I'm typing it into my calculator, because You're probably faster than me. Oh no, you're not faster than me. 1077. Why have I written temperature? Oh yeah, that's right. It is temperature. Kelvin. There we are. It has contracted because it has cooled. Yeah, I think something might have gone wrong there, Pranav. Chuck it back at your calculator and see if you get the right answer. Your instinct is good here. You know, trust your instinct. If you start getting numbers that just don't seem to make a lot of sense to you, chances are it's because they're wrong. So, question 3 then. We've had one on Boyle's law. We've had one on Charles' law. Charles' law is an A-level equation. We're now going to have the last one, which is about the pressure law, and that is a GCSE equation. I think I know, Pranav, but people are going to get tired if I keep on saying the same thing. So we're given pressure, temperature. So this is a constant volume situation. This is the classic pressurized tank, which the volume doesn't change, but you chuck it on a fire to make it hotter. That's right, Pranav. Everything you did was right until the calculator took over. So you need to remember here for the pressure law that pressure is directly proportional to temperature as long as temperature is measured in Kelvin. Fortunately, temperature is measured in Kelvin, so we don't have to convert the temperature first. These are all the things you have to check. And so the temperature afterwards divided by the temperature before. If you can design one, I'll use it, I promise you. And then multiplied by the pressure before gives us the pressure afterwards. Okay. And you can probably beat me to it. Oh, apparently you can't. So it's 332,000. Near enough. I didn't quite get that, Mateus. No, I didn't quite get that. I got 332,252. I just rounded to 3 significant figures. Now, is that because I've typed something wrong or because you have? So 30, well no, I might have typed it wrong. 4179, because I was rushing. 4.536E5. Yeah, that time it was me. No, yours is fine. That time it was me. Happy with that, Mateus, well done. So there are the 3 experimental gas laws. Done. And you can check the answers if you go on to here, and hopefully if you click on answers, you get the answers appearing here. Yeah, that's what we've calculated, and off you go. So what I'll do, I'll stop there. Next week, I think we'll start by just doing a couple of these to start with. We won't have to do unit conversions again, but I'll try to get some where there are some unit conversions built into the question, hopefully. Can't see that many there. F9, maybe we'll get some more at some point. And then we'll move on to some exam questions, courtesy of the only exam board that's given me permission to use their questions. See a few people typing messages there. So I do hope that's been helpful. Yeah, sorry about the false start with the camera. I will fiddle around and try to get it to be the default. I don't know why it bounced it across, because it was working before I walked away, and then it stopped 10 minutes later. And I'll fiddle around with my microphone and get those settings back the way they were as well, because I think I know what I need to do there. So I apologise for the bad sound quality, and please tune in next week for the conclusion of gases. Thank you very much.